Alright, so today we are talking about matter and temperature. Actually,
Why are there 4s on the board?
Ethan. Ethan, activate manual breathing mode so then everybody focuses on their breathing.
Sounds like a terrible idea.
Just by saying that.
Thermal expansion. What's thermal expansion?
Before your test corrections away, I will let you work on them later, not right now. I see you working on them while I'm taking the test.
No.
I don't think about that. Okay, so matter and temperature. I'm going to wait until you're ready, then we will continue.
Not against this is not my physical side.
And by ready, I mean quiet and not tapping things and making noise. Still need you to stop.
Stop.
All right.
Five.
All right, let us begin. Matter and temperature is what we're talking about. Pen. All right. What are the four states of matter?
Solid, liquid, gas, plasma.
Solid, liquid, gas, and plasma. So, those are the four states of matter. They all depend on what factor? The temperature. Correct. Now, examples. What's an example of a solid? Ice, like liquid water that's been frozen. That's what it's called. Liquids are generally warm. Gas is generally hotter than that, such as steam or the gas that we breathe out of the air. Now, this is sort of a review. We've talked about this to some degree in our heat and temperature discussion, so I want to go through this as quickly as we can so we can move on to things that are more interesting, which you don't know. So, gas. What is the characteristic of gas?
More energy.
More energy. The particles are closer together or farther apart than the others? Farther apart. And they have complete freedom of motion.
Wow, okay.
So they are free to move around each other. They don't actually interact with each other very much. And there's a lot of empty space. Okay? For liquids, is it more ordered or less ordered than gas? It's more ordered than gas. Lindsay, I see you leaning back in your chair. Please put it down. Disordered. Okay? Particles or clusters of particles are free to move relative to each other. So they can move, but they don't have nearly as much space as gas. And the particles are all close together, i.e. less space. All right. If you talk about crystalline solid, this is the most ordered. It is a very organized structure. The particles are essentially in a fixed position, and these particles are very close together. So the particles don't really move that much. They vibrate some, but they don't change location, particularly in a solid. As you'll notice, you have a rock. A rock doesn't exactly change its shape very much, right? It's the shape of the rock. And then you can do corrections on them. Not during class today, but you can do it tomorrow as homework. Elena, if you're working on corrections, please stop and pay attention to lecture. Okay, just checking. All right, so I'm going to wait till everyone's paying attention, and then I'll continue. I need your attention up here, please. All right. Yes, you can correct them today, but not during class today.
When can you correct them? When do you have to?
It's due by Wednesday.
What is 32 out of 36?
Do it on a calculator. I don't know. All right. So, not right now. Not right now. We need to be paying attention to lecture. Please pay attention to lecture. This will only last a few minutes. This is actually a pretty short lecture. I only have 4 more slides. and then we'll move on to something that you might be able to pay more attention to. All right, solids. They have a definite shape and a definite volume. There are a couple of different kinds of solids. A crystalline solid has a repeating crystal structure.
What?
And that crystal it's a crystal arrangement and it's repeating. And so it might look like, where's the structure? So here's an example of a crystalline SiO2. This is a very consistent structure. It is the same throughout and has a specific organized structure. Yes, Lindsay. It's a candle. It's a candle. So an amorphous solid is the other kind of solid. There is no crystal arrangement, and you can think of this as like thick liquids, such as waxes or glass or various things like that. Those do not have a specific structure. They're kind of loosely organized in some random organization of structures. Okay? Example of that is a candle. Other examples could be glass windows. If you see really, really old glass windows, you'll see that they actually are they're thicker at the bottom than at the top because they've actually started flowing. The liquid has started flowing down. It's kind of or the solid has started flowing down. It's kind of strange.
Wow.
Yep, it takes a long time though. All right, so liquids. A couple characteristics. They have a definite volume, but they do not have a definite shape. Okay, they can take the shape of whatever container they're in. All right, they can flow or be poured because the particles can move around. And in gas, what are the characteristics? No definite volume, no definite shape. So if we go back to solid had a definite shape and a definite volume, correct? Definite shape and a definite volume. A rock has a specific shape unless you change it by mashing it with a hammer. Okay? Liquids will still be solid at that point. Have a definite volume but not a definite shape. I'm going to wait. All right. Gas has no definite volume and no definite shape. So that's one characteristic you need to remember, the differences between them. All right. They move far apart in all directions. So they kind of move whatever direction they want, and they move far apart. Now, example of when we can compress air is one of these dust removers that we use for computers. We have compressed air in there, and as we squeeze the trigger, it expands and pushes out the nozzle and sprays onto the thing we're trying to remove dust from. All right. The fourth kind is a plasma. This is a gas-like mixture of positive and negatively charged particles. Okay? So, mixture of positively, please stop wasting my tape. I would like to use it for other things. Thank you. Gas-like mixture of positively and negatively charged particles. Most common form of matter in the universe. Why is this the most common form of matter in the universe? It's in the stars. It's in nebula. Most of the planets are similar to plasmas. Well, actually, take that back. The stars are plasmas. The planets are generally not. They're usually gas, solid, or liquid. Okay, so particle collisions are violent, very violent, and they're found in stars and fluorescent bulbs. Violent, the particles smash into each other a lot. Okay, so notice up here at the top, what's that picture on the top right? That's the sun. And then the fluorescent light bulb is before. So we actually have plasma in the room when we turn on the lights.
Would we die if we broke all the light bulbs?
Probably because of the mercury, not anything else. Yes, Lindsay. Same as the speed of light. Same as the speed of light. As soon as light is gone, then the darkness shows up. All right. The other thing that's important for this discussion is talking about thermal expansion. Okay. Notice it says here, most materials expanded when heated and contract when cooled. So if I take, let's say that I take a steel bar, okay, and I heat it up, what will happen to it?
It'll get hot.
It'll get hot.
Gravity will reshape it.
I think tower expansion is in the summer.
Ow. Oops. I have some toys.
Eiffel Tower is 6 inches taller than summer.
Are we gonna heat this up?
You would if you're on top of the Eiffel Tower.
No.
Oh my gosh, she's such a color.
So, in my hand I have two objects.
No. My microwave is over here. No problems.
Like the centimeters. You would slam it into the car.
So, I have two objects here. I have a ball and a hoop. Right? A ball and a hoop. In basketball, you like the ball to go through the hoop, right?
No.
So,
You're gonna want
all right. So here, see if you can get those to go through each other.
But if you cool it down.
No, you didn't.
Okay. So it's very hard to get through, right? Now get it back on. Okay. So it's harder to get through in that case.
Wait, what?
Now.
Wait, no.
Ladies, are you watching?
It is.
What just happened? He's moving. What's he moving?
An object.
An object.
Your
And what's
toy.
he doing? Okay. And what is he doing with them? What are the two objects?
Wow.
Yeah.
There we go.
Haha, well, proud.
All right.
It's a
We have one object. We have a ball and a hoop. Right? If you work at it, you can get it to go through. Right? It's hard. Actually, that's pretty hard to get through.
Sorry, fan. What?
Wow, what is this straw?
Oh.
Now we're
Oh.
You need to set up.
Twinkie truck. All right. So, with some work, you get it to go to the hoop to go through, or the ball to go through the hoop. Now, this is the back, please. All right. Which one would you like me to keep first? The ball first.
No, you want to keep the hoop for her. Now the ball. Good job, guys.
All right.
Wait, put cool on there. Oh, you broke it. What? I have one point. I have that mic.
Wow.
Guys,
Buy one of your own.
I can buy one.
I'm white like on the shoulder, right?
It is much. It won't go in. I can't even get it stuck.
Let me try.
No, you're
Ball.
all right here. Okay? Now, what do you do? Now, if I need up the hoop, anything will happen. It'll stand and we'll put the ball.
Put the ball in water and then the food.
Oh, it'll pull off on you.
Wait, what?
Google in 2009 hired
Simple time. Now, it's very easy for me to pass the ball through the.
What do we get?
Well, I think that this one is expanded. All right, now. To further explore this phenomenon, keep your attention up here, please. And keep your attention up here. Up here. All right. Next person I see leaning back in the chair needs to lose the chair for the day. Sorry. If you are on more than one, if you are less than one, I will be taking
Wasting tape.
Where did I put it?
Wow, I feel so much shorter now. I'm probably more.
We are watching a video.
No, that way I can went down. Wow. Is that like a big guy? There's so many there. The black one loads faster. Hey, why is the front screen white?
All right. Attention, everyone. Pay attention to the screen. He is not singing. Buffering. Hold on. Make sure I'm at 240.
Oh my goodness.
Ladies and gentlemen, I'm hearing a lot of talking during this video, which I want you to pay attention to, so I get to go start over since you guys are not paying attention. So please listen. I really want to help you learn this stuff, and if you're talking in the midst of it, I don't believe that you're learning, and so it's hard for me to tell. He's getting to it. Okay. That's the point. Okay. How did ice skating rink? Someplace in either England or Canada. I'm not sure which, or Australia. I said it's possible too. So here's actually a really cool experiment that they did with. Oh, come on, go back.
Vertical straw.
This one I think was really cool. If we can get it to load. Apparently, the internet's being stupid today. Yes, Joey, you have a question, or you just stretching?
Oh, we're like pros. No.
All right.
Stupid.
Then
Oh, same guy.
same guy.
Oh.
Hey now. I'm just close my computer. I think it's probably the. I bet I know what it is. I bet it's the screen capture program. Stop.